Hey folks, this is lecture 5 for Geomatics 310. We're going to go through coordinate systems today. There's a lot to discuss here. I will admit that this is one of those topics that is hard for geographers. A lot of surveyors work with this material every day. But from the GIS side, sometimes it can be a little bit new and confusing. So I'm hoping to explain some of that as best I can, and hoping to answer some questions about how these things fit together. So a coordinate system is a choice of values and units to store for a data set. Um, these occur in a coordinate space, which is an agreed upon range of coordinate values. And so when you talk about components of that coordinate system, you have units and values. And so units are things like feet, meters, decimal degrees, degrees, minutes, seconds. And then the values for those look like the following, which is like 124 feet, 11 inches by 77 feet, 3 inches. That would be like a coordinate location on a plane. So the definition of a point. A line would have multiples of those strung together. So that's kind of sort of the basics of what a coordinate system is. But when we think of coordinate systems, we tend to think of them in a more standardized manner. And so a standard coordinate system is a coordinate space whose characteristics are defined and established according to cartographic standards, and it's tied to a specific location on the Earth's surface. And so that graphic at the right would actually be anchored to a well-known position on the Earth's surface at 0, 0, and then your coordinate system would then expand off of that. Some of the best coordinate systems, the best model of the Earth, which coordinate systems help to define, the best model is a globe because that closely approximates the exact shape of the Earth, and it's in 3 dimensions and it's easily understood. The drawbacks to using something like that is you kind of can't carry around a globe with you in your pocket. It's not good for making measurements. It's just hard to work with. So people will try different options for doing that. One of the most well known is just the Geographic Coordinate System, GCS. It's based on spherical globe coordinates, and basically when you see the descriptions of it, it's described in degrees of latitude and longitude. Longitude measures horizontally in east to west with a prime meridian. And then you have latitude measures, which are your parallels, and they measure vertical angles above or below the equator. And you can see how they're described here with longitude moving east to west and latitude moving north to south starting at the equator. And so that's how we basically locate positions on the Earth's surface is by those measure values. Here you see another way of looking at it there with the angles actually spinning off the center of the sphere out towards the side. So the ones that are moving north to south are your degrees of latitude, and the ones moving east to west are your degrees of longitude. They're measured in both north and south. You'll see the S and the N for south and north, or W and east for west and east off of that prime meridian. So very easy to understand concept of kind of how that fits together. Um, but the Earth is not a perfect sphere. We're actually a little squashed down egg looking thing when we're spinning in space. And so we actually refer to that modified shape here, this is in the red box, as a spheroid. And it's a generalization of a sphere. So it's kind of making an estimate. And a spheroid is the best fit to the Earth's true shape. And it assumes that the Earth's surface is smooth, when in reality, we know that the Earth's surface is undulating and got a lot of like imperfections to it. And we'll talk a little bit about how that works a little bit later in regards to the geoid. But the spheroid can be defined by the length of its semi-major axis and semi-minor axes, or by the length of its semi-major axis and a flattening value. And you see the formula there to the right. That basically describes that so that you can perform some mathematical operations upon it. Geoids are actually a improved version of the Earth's surface. It is not meant to be exact. It uses a lot of gravitational measurements and calculations, but it is currently the closest approximation to the Earth's surface. It's considerably smoother than the Earth's actual physical surface, which would be more of like a topographic map or a topographic, exact rendering, but it is close. And it basically defines zero elevation derived through complex math and gravity, like I was saying. And this model is used to measure surface elevations with a high degree of accuracy. So that's what you see there in that red box. Datums are something that is confusing for a lot of folks. And what exactly is a datum, and how does this actually all fit together? So this is one that may take a little bit of thought around it. But datum is like a recipe. A datum specifies which spheroid you're using. Um, and so to take a step back, a datum is something that has components to it. It's not just, one item. And so when we talk about a datum, like a recipe where you would add eggs and salt and sugar and flour, here you add different things, and you add a spheroid to the mix, and you add a few other things like the geoid and how they tie together. So we'll go through that here. A datum specifies which spheroid you're using as your Earth model and at which exact location you're aligning that spheroid to the Earth's surface. And so because the geoid is too complex and irregular, the spheroid is used as part of the datum. And so essentially what you're doing with the datum is you are tying that geoid to the spheroid, and where it is most appropriate is where that location point is being spoken about. So you think of those as like a benchmark where the spheroid and the geoid come together. That's where you anchor in the two, and it helps you in a localized fashion be able to orient your coordinate system on top of that spheroid. And so when you're talking about which spheroid to pick, you usually use one that is appropriate for your local area, because particular spheroids work really well in particular areas of the Earth's surface. Some will fit good overall, but some spheroids will actually do better in certain parts of the Earth's surface. So you can see on the left side there, one spheroid seems to fit the geoid better in North America. Another one seems to fit better in Europe. All the way on the right, you see one that sort of does a good job of hooking up the two overall. And so that anchoring in the center there is that datum, and how that thing all fits together is really anchored off of that one point. And then from that one point, you can then orient the spheroid accordingly, which then your geographic coordinate system fits on top of. So just to continue there, the datum therefore defines an origin and orientation of the geographic coordinate system. The origin is the point where the spheroid matches up perfectly with the surface of the Earth and where the latitude and longitude coordinates on a spheroid are true and accurate. All other points in the system are referenced to that origin. In this way, a datum determines how your geographic coordinate system assigns latitude and longitude values to future locations. So it is a complex problem, a complex topic. So I would read through those bullets maybe a couple times to kind of ingest that, because it's one of those things that can get you if you don't quite understand how a datum and a geoid and a spheroid all kind of play together. And so I always look at it in the sense of saying, my geoid is the most accurate, but I can't use it because it's almost too much information. And so I got to figure out a spheroid shape that closely approximates where that geoid fits in. And sometimes I may use one that just the spheroid is better for me locally, or sometimes I might use something where a spheroid that fits well all across the world. And I make that choice based on the level of accuracy I wish to achieve. And then the points that tie in are where those datum origin points are where the geoid and the spheroid match up, and they're true at that one particular point. And so that is the recipe. It's that anchor point, it's the spheroid and the geoid kind of all coming together to orient your spheroid where you lay the coordinate system on top of. Some common datums you'll hear mentioned a lot. There's a North American datum of 27, 83. They'll say NAD 83, NAD 27. NAD 83 is one that we're currently sitting in. That's not going to be around for much longer. We're actually moving to a new datum, the year 2025 in the state. So you see some of that change. And then you also see the WGSA 4 datum. That's a geocentric datum. You see that mentioned a lot when it comes to using your GPS or capturing latitude, longitude values out in the field. That's sort of like the default when it comes to that. And if you need to move between datums, so if you want to move from a datum that's better for the world like we were talking about. You have a spheroid that has a coordinate system on top of it tied to the geoid, and you're using one for the world like you would if you're using like GPS, and you want to move to one that's local, so like NAD 83 for the state of North Carolina. What you would do is you would perform a transformation, which is essentially changing those coordinate values to match up with that new localized location that's all tied in. So when we talk about some of the things we're going to talk about in the future, transformations are often applied to move the datum from one to another during that reprojection. We'll talk about that in a little bit more detail. In addition to geographic coordinate systems, there's what we call projected coordinate systems. And so when you have your geographic coordinate system established, which you see there on the left, it's sort of like the spheroid with the coordinate system laid over top of it, and you want to actually see that on a flat map, you go through the purpose of projecting that line work, essentially that net that's over top of the Earth's surface that's forms that latitude and longitude grid, kind of unfold that surface into a flat plane. That's what we call projecting. Essentially putting a light bulb in the center of the Earth's center and then letting the light kind of travel out through those grids and seeing how that lays out on a flat surface. There's all kinds of ways to do that. And it's a lot of math. We don't need to get into all the math here. But the important thing to remember is different projections that we use in our world of geography and GIS and surveying, they're used for different areas and purposes. And so we'll talk through some of those here. In any projected coordinate system, there's always going to be distortion. The type and degree of distortion varies with a different type of map projection. We'll talk about that in a minute. And so we must choose one that's suitable for the needs that we have. In any projection, there's no distortion, however, where the line on the globe touches the plane of the projected surface we're putting the projection onto. So here's a couple of examples here. So here you see the three basic what I would refer to the common projection methods. The top is the cylindrical, where you have, imagine the cylinder there is a piece of paper, and you're surrounding the globe with a light in the center of the globe, and you're shining the light out. The light passes through the surface of that globe, and then it projects, to use the word, projects those grid values onto the paper that's surrounded that globe with the light in the center. And you see to the right, when you unfold that piece of paper, you end up with a grid that goes north and south, and it projects onto the paper. And there's a lot of maps you see through growing up that are on the wall or in textbooks and things like that. They're Mercator projections. That's that example of a cylindrical projection. You can also use conical projections, Lambert equal area. The one we use for state plane coordinate systems at times is a conical projection. Here you can see that the cone fits down over top of the Earth's surface, and you can see in two spots that cone touches the surface of the Earth. That's where the accuracy is going to be the greatest. In the example above, where it's not really greatly shown here, but where that cone would come in close contact with the Earth's surface, not cone, that cylinder would come in close contact with the Earth's surface, that would be around the equator in that above example. That is where you would see the best accuracy there. And then in the bottom, you have what's known as an azimuthal projection, or in this one, they call it orthographic, where the plane that you're projecting onto really only touches the Earth surface in one spot. And at that particular location, that's where the highest level of accuracy is. Here's another way to look at it here. A little bit more information. You can see the cylindrical projection is shown a little bit clearer here, where it touches at one point around the equator. Like I said, that's used for the Mercator projection. That preserves direction and the shape at the expense of distance and area. So your areas look all whacked, like the maps that you see where you have like Greenland's very huge, but it's actually really the size of Mexico, but it looks like it's the size of Africa. That's sort of like the distortion of shape at the expense of distance and area. The conical projection, which you see there in the middle, that touches in the higher latitudes. So that's if you're going to map areas that are a little bit higher up above the equator. They actually do a really good job locally of having a lot of really excellent accuracy shown. They preserve distance or area at this space at the expense of shape and direction. And then the final one is the azimuthal projection, which preserves area or distances at the expense of shape and direction. So shape and direction is best, better served at yeah, I'm sorry. Yeah, the Mercator projection is going to do a better job with direction and shape, where the azimuthal might do better at area or distances in that particular area of the projected surface where it touches the surface of the Earth. Um, so when you're looking at that, and you're like, how do I determine which projection to use? Here's some tips that a lot of people use, like conformal projections for topographic maps, navigation charts, weather maps, equal area, dot density maps, thematic maps. That preserves the areas, makes it a little bit more realistic looking. Um, Equidistance, if you're doing like airline distances or seismic maps, things like that, that preserves distance from one or two specified points to all the other points on the map. Um, Azimuthal, where the surface touches one place, they're good for navigation and route planning. And then there are compromise maps where it's no point is completely distortion free, but you're basically trying to make it look as good as you can. That's something that you would use for world maps. And there is a whole litany of these different types of projections in the ArcGIS Pro software you can pick from. And sometimes you just want to experiment a little bit. It's okay to do that. Um, Distortion is inevitable. And whether you're working with world, or continent, or countries, or local, there's always going to be something that's not quite right. So you really need to make sure that you're choosing something that is best suited to the objective you're trying to achieve. um, Common projection systems that you see relatively often. I see these every day in what I do. There's a GCS, which is basically just your latitude and longitude against the spheroid with a datum. The UTM, which is the Universal Transverse Mercator, which divides the world into 60 zones. You'll see that in a second. That actually turns the cylinder that we were looking at touching the equator on its side, and it has the cylinder with its points touching essentially along the lines of longitude as opposed to latitude. And then you'll see the state plate coordinate systems. They're called coordinate systems, but they're actually what you would refer to as a spatial reference. These are used for localized mapping at the state level and at the county level, and they divide states into one or more zones. And for larger states, you have more than one zone. So you'll see a lot of times when you're mapping states, either the UTM used or the state plane coordinate system used. That happens quite a lot. You don't see the GCS used when you're mapping states. GCS tends to not have a projection associated with it other than just kind of unloading it. If you're going to like take the data and ship it somewhere, you can use it's it's late noted in a later slide, but very rarely is that ever used for like mapping. Usually most cases you're using UTM or a state plane coordinate system. For the GCS, oh, that's what it is. It's equirectangular projection, and a lot of times you're just shipping data from back and forth when you're using the GCS. A lot of times you obtain the data, you project it into the desired coordinate system for the application. And so basically what I'm saying is you capture the data and the GCS coordinate values, you've got them. If you wanted to see them on a map, you could use an equirectangular projection, but a lot of times you're storing those values and then you're going to reproject those values from the GCS into something more applicable to your area like UTM or the state plane coordinate system. Because if you left it in the GCS and you tried to push that out as an equirectangular, you end up with stuff that just doesn't quite make sense. Like I was saying earlier, the UTM projection, Universal Transverse Mercator, is based on the transverse Mercator. Is based on, yeah, the transverse Mercator cylindrical projection, but the world is, you can see down here on the left side, you can see that the cylinder is actually turned on its side and the center of the cylinder touches lines of longitude as opposed to lines of latitude. And the world's divided into 60 zones. And distortion is minimal within each zone. That's true. That's why you see longer states or big states tend to use UTM to divide the state up. It's very, very useful, especially out west. For smaller states, usually state plane works better, but UTM is a nice projection when you're dealing with larger, longer areas along lines of longitude. And they're best for covering a small area in one zone. So I'm thinking about like a state, as being, a smaller area in one zone as opposed to like an entire country. That's kind of the way we're looking at it here. The state plane coordinate system, you can see a map of the state plane coordinate zones on the right there. You can see that some states have multiple state plane coordinate zones. The states that are divided into more than one zone tend to use different um, datums or projections depending on what they need to do. You can see that a variety of different states have multiple zones, and the projection and parameters are established for each zone to achieve the desired accuracy. So you can basically say that they're shifting the datum, they're shifting the origin points, they're doing things with those different zones to get the best performance of the projection in different parts of their state. So it's really interesting to see how different states do it. State like Montana is gigantic, has one huge, similar projection system for the entire state. But you look at Texas, they have zones moving north to south. Longer states like Alabama have moving north and south as well, but they only have two. They're moving, better way to put it, their longest north to south, where in Texas, they're longest east to west, those zones. So it's fascinating the way different states break it up. Um, and you'll see, all kinds of mix and matches of transverse Mercator, Lambert Formiconic, or oblique Mercator, depending on what the state feels is going to give the best results for their localized area. So in the state of North Carolina, we're using state plane coordinate system, and we are using the NAD83 datum right now in the US survey foot, if I'm not mistaken, as far as the units go. And right now we have one area. We're actually moving to two, I believe, in 2025. So that's pretty cool how they're changing things around for us to get a little bit more accurate. I find this topic, pretty fascinating. Here's another look at it here. But what's important to remember is that while we're talking about coordinate systems and datums and spheroids, they all basically fit into something called a spatial reference system. And that is what you will see in ArcGIS Pro. You'll see reference to reference, no pun intended. You'll see a note of a spatial reference when you look at the metadata or the source. It's actually source, yeah, source there on the right. The source has listed inside of it the spatial reference. And so, excuse me, to choke up there, a particular spatial reference system will list the spheroid. It'll list the horizontal datum, the projection it's using, the origin point, and the unit of measure. And so what you'll see for a lot of these, like we were just talking about, if you think about how projections work, you'll look at the geographic coordinate system, which is the sphere on the spheroid, and you'll see that it has a datum associated with that. And so that's where you start. And so for that datum, the WGS84 datum, that is a worldwide datum that suits the surface of the Earth best. If you were going to use a localized datum like NAD83 or something like that, you would see a different spheroid chosen probably, and you would also see a different datum chosen. So right there, you see WGS84 in the spheroid, and then you see the datum, which is WGS84 as well. If you were choosing something like NAD83 as your localized datum, you would see the spheroid would probably be a different representation than the WGS84. You probably see something like GRS80 or one of those, which is better suited to our localized area for a representation of the Earth's surface on a spheroid. So you start with a geographic coordinate system and how you're applying that grid to the sphere. And then there's a projection on top of it. So the top part here is what you're using to show it in a planar manner. And you can see that the projected coordinate system is the UTM zone north 18. It's using the same geographic coordinate system information down here, but it's applying the linear unit to it. It's telling you the latitude of origin, and it's telling you the central meridian. So this is centered at 0, and at -75 in the longitude. And then here you have whether there's false easing or false easings or northing added to it to offset that grid to make it easier to have positive values. And then it tells you it's measuring it in meters. So that's sort of the information that you see here in the spatial reference. But like we just reflected upon in our slides, it's a combination of all the items that make up that spatial reference system. So it's the spheroid, the datum that they're choosing that is, linking the geoid to the spheroid. Then there's the map projection, which takes it from the spheroid to the flat surface. And then the origin point for where that your coordinate system sits, and then the unit of measure that the coordinate system is using, whether it's feet or meters, et cetera, et cetera. So very cool how it all fits together. Like I said earlier, the choice of projection depends on the objective of the map. And once again, just to reinforce that, you choose the appropriate system for the task, whether you're looking for true distances, direction, size, etc. And it's especially important for spatial analysis. I want to make sure I reinforce this here is that you want to make sure that um, you're picking the coordinate system and, well, let's just say the spatial reference. You want to pick the spatial reference that limits this distortion as much as possible when you're analyzing data if you're looking at the data geographically. If you're just analyzing data in a table, you know, the projection system doesn't mean anything if you're just trying to figure like how many people live in a polygon. But if you're looking for the area of the polygon and how many people are across, so many square miles, or if you're looking for lengths of roadway or railway, you need to pick a projection system, spatial reference system that matches very closely um, with the level of accuracy you're trying to attain for that particular area. So um, you have to do a little bit of research and you have to know. And that's what makes us professionals in the field is we kind of have that research under our belt to know which ones are best for different tasks. So that is really a big key. One perfect example that I can recall early on in my career, we had a lot of field mapping we were doing, and that field mapping was done in WGS 84 in a sphere, and we brought that information into GIS. We summarized the information right out of there, and we got values that were different from what they were finding using state plane coordinate system with a localized datum that was much more accurate. And so there was a very quick discrepancy there, and people were wondering how we were differing. And so when they brought it in front of the professionals, we were able to quickly ascertain, hey, you shouldn't be using GCS to get your measurements on that WGS84 data. And really what you should be doing is, reprojecting that data into the localized datum, um, so that into the localized spatial reference using that localized datum in order to get a better result. And so it comes up all the time. It'll sneak up on you and grab you from time to time. And it's not unusual for even seasoned professionals to miss that. But the important thing to remember is that you should always have a way to check yourself. Um, so knowing true measurements in the real world and then checking them against your projections data just to make sure that what you're getting matches up is always a good way to go about doing things. So yeah, definitely spend the time to research the best options for the type of task you've been presented with. In relationship to ArcGIS Pro, a couple things. There's a function in ArcGIS Pro which is called projecting on the fly. It's important to note that what that means is that you've got data that's stored as part of its source. So if we were to go back to our, let's go back to our graphic here. We'll scroll back. So in this spatial reference, most data sets have a spatial reference system associated with them. And ArcGIS Pro can read this, and it knows that you want to see all the data together. And so it will think, okay, well, let me make some assumptions for you. And so the first data set you load in, which we'll talk about it again in a second, it'll load that as like the primary coordinate system for your map. And then it'll look at the other data sets that you've loaded in and their differing coordinate systems, spatial references. And it will look at those two and to figure out the best way mathematically to bring those together for you to make your job easier. And so we'll do that what they call projecting on the fly, where it takes the second, third, and fourth data set that's loaded into your ArcMap and it will reproject those in real time on top of the first data set that was loaded. So if your first data set was like GCS WGS84 and that's what you loaded in, that's the spatial reference it starts with. But then your next one is something in state plane, and then your following one is something in UTM. It's going to reproject those to make sure that they all line up as best as it can manage so that you have a map that you can bring that makes sense. It's extremely useful when you're making data, making maps with data that are different and you want to show things quickly, but it can catch you when it comes down to like spatial analysis. So you have to be careful about that. Um, the initial coordinate system for any ArcGIS Pro document will default to the first data set added. So like I was just saying, like if your first data set you add in GCS or state plane, like all the other data sets are going to be keying off of that so that things show up correctly. It does not change the underlying data. And that's very important. And so you have to be careful that when you're doing spatial analysis, you should really try to get all of your data projected into the same spatial reference, so that when you do your analysis, the analysis agrees with itself essentially. Um, because when you start looking at the data separate from one another and you try to make apples talk to apples, it becomes very difficult. So you want to use the advantages that the software provides you to bring all the data sets into the same spatial reference. Um, if you don't have a spatial reference defined, which does happen from time to time, and that spatial reference box is basically listed as unknown, when you bring that data in, ArcGIS Pro will look at the data that you have stored in there, and it will look at the values, and it will try to make an educated guess about where that belongs. It just has basically a matrix that says a lot of times values that are these for my features, when they fall into this, it's probably UTM or probably state plane or whatever it is. Um, ArcGIS Pro will make a guess, and a lot of times that guess is correct, and sometimes it's wrong. So you just have to be careful. And I'd stress that you read page 120 to 122 in the book. There's some excellent points in there that you can read. I don't need to reiterate them here. But much like I said, using that same spatial reference when performing analysis is really important. And ArcGIS Pro has defined rules for the assumptions it makes. And so, like I was saying, with the first data loaded, that becomes the coordinate system for the map. And um, that defines the datum and the spheroid. All those things that make up the spatial reference are assigned by that first layer that's loaded, and everything else kind of piles on top of that. It'll also do different things regarding how it processes that data as well. So take a look at page 120 to 122. So yeah, that's really pretty much everything I have to say about coordinate systems and spatial referencing and datums and spheroids this week. It is not easy. So if you don't understand it at first go around, I encourage you to maybe listen to the presentation again. Um, there are some YouTube videos out there that if you just type in like, how projections work or things like that, there's some really good ones that I found on YouTube that explain it. But the thing that I would focus on that I did not see a lot of places though is this slide here, which is referring to datums like a recipe. Um, this is really important just to remember in the back of your head when people talk about what datums are. It's really a recipe for how that coordinate system will lay out on a sphere and why that kind of all fits together correctly. So this is a really good slide just as a note for yourself to take a look at, repeatedly when you're kind of like, what's a datum again? And it's that combination of spheroid and geoid and coordinate system that lays on top of the spheroid once you've picked the um, geoid and spheroid combination that works best. So yeah, great stuff. It's really interesting. It really plays out in the real world just like it pretends to. So I would simply say, take your time with it. Come back around to it multiple times. If you have any questions, you can always give me a holler. But yeah, thanks for listening this week. And if any questions on the assignment, please let me know. And yeah, let's keep moving forward. Thanks a lot.